In this problem, we're looking at a block being shot up a ramp by a coiled spring, and we're interested in two different questions here. We want to know the speed of the block as soon as the spring is extended back to its natural length. And then the second part is we want to know how far the block slides up the ramp before it comes to a stop. So we're given all the specs here. The spring constant is 735 newtons per meter. The angle of the ramp is 32 degrees. The mass of this block, 1.5 kilograms. The spring is coiled by 20 centimeters relative to its natural length in the initial state of the problem. And we start out by computing the speed of the block at the moment that spring is extended back to its natural length. So this is an energy conservation problem. I can write E initial is equal to E final. And in my initial state, all the energy is in the coiling of the spring. I'm going to choose to put a y coordinate of 0 at that initial spot so that I can say there's no gravitational potential energy initially. So I have 1/2 k, and I'll just call it x naught squared for the initial compression length. That's all my initial energy. Again, that depends on putting a y coordinate of 0 at my initial location. So I'm measuring the height of the block at its lower left corner, and I'm saying my initial height was y equals 0. And now we need to figure out what's the final height of the block. And here I have a hypotenuse of length 20 centimeters and an angle of elevation of 32 degrees for this triangle. So my final y coordinate is the vertical component there. It's going to be 20 centimeters times the sine of 32 degrees, or I could write it as 0.2 sine 32. So I go back to my energy conservation equation, and in the final state here, I have kinetic energy, 1/2 mv squared, and it's the v that we're looking for. And I have gravitational potential energy, and that's going to be mg times y final, where y final is 0.2 times the sine of 32. Now I should be able to just plug everything in and solve for v. So I get 1/2 times k, which was 735. Initial compression distance is 0.2, and I need to square that, so times 0.2 squared. That's equal to 1/2 times the mass of this block, 1.5 kilograms, times the speed of the block squared, that's what we're trying to solve for, plus the mass of the block, 1.5 kilograms, times g, and we'll use 9.8 for that, times y final, which is 0.2 sine 32. And you can handle this all at once in a scientific calculator. I just multiplied all the numbers on the left side, then I subtracted the product of all these numbers in my potential energy term, then I multiplied by 2 divided by 1.5 and square rooted the result. When we run all these numbers, we get a speed of 4.19 meters per second. In part B, we're trying to find the maximum distance d that the block slides up the ramp. And notice in the picture, this was defined as the distance from the equilibrium location of the spring up to that highest point. So it's not the total sliding distance from our initial location of the block on the compressed spring up to the highest point. Now there are a variety of ways of handling this problem. We could take the answer to part A as our initial velocity and then do this just using kinematics, as long as we're able to compute the constant negative acceleration on the way up. Or we could use energy conservation starting from the part that we computed in part A, where the energy is all kinetic, and then that's gradually transformed into the final potential energy. But the way I prefer to do it is to just go all the way back to the initial state of the problem where all the energy was in the coiled spring, and then in the final state, all the energy is potential. So again, I'm going to put the 0 of my coordinate system at the initial location so I don't have to worry about initial gravitational potential energy. And when I write E initial is equal to E final, what I mean by the initial energy is just the energy stored in that spring, so 1/2 k x naught squared. And in my final state, while I'm measuring relative to y equals 0, that initial location of the block, in my final state, I'm going to have a height all the way up here that's again given by the hypotenuse along this ramp multiplied by the sine of 30 degrees. Well, the hypotenuse now is d plus 20 centimeters. So my final y coordinate is going to be d plus 0.2 times the sine of 32 degrees. So I pop the potential energy term into my energy conservation equation. And in my final state, that's all the energy there is. So I have mg times the final y value, which is given by d plus 0.2 times the sine of 32 degrees. Now we just plug all the numbers in, and I have 1/2 times k, which was 735. Initial compression distance squared, so 0.2 squared, is equal to 1.5 kilograms for the mass times 9.8 meters per second squared for g. D is our unknown, so I have this d plus 0.2 term times the sine of 32. And again, I handled this all at once in my scientific calculator. I just multiplied all the numbers on the left and then divided by 1.5, divided by 9.8, divided by the sine of 32 degrees, and then subtracted 0.2, and I got D. And this sliding distance comes out to 1.69 meters. And that's it. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.